Hello guys, welcome to episode 1 of Road to 50 Mohs. So today we will look at this problem from USAMO 2012 problem 1. This question is a 0 Mohs question, so let's get started. So the question says, find all integers n larger than or equal to 3 such that among any n positive real numbers a1 to an with max a1 to an is less than or equal to n times min a1 to an, then there exist 3 that are the side lengths of an acute triangle. All right, so important parts is, so any n, and then max, this condition must be true, and then there exist 3 that are the side lengths of an acute triangle, so acute, double highlight. All right, so first of all, let's assume that, we assume that there exists a sequence a1 to an satisfying the max a1 to an less than or equal to n times min a1 to an condition, but no 3 are form the side lengths of an acute triangle. So basically we're looking at the negation of this statement, this question. So the question is asking for you to find that there exist, but we look at there does not exist. All right, so, and also without loss of generality, we can say that the list is ordered in this way. An. All right, so the first thing you should know about acute triangles is that for any triangle, acute triangle, make it bigger, S with side lengths S1, S2, S3, this equality must be true. So S1 is less than S1 squared less than S2 squared plus S3 squared. And this kind of comes from like the Pythagorean theorem, where it's like if you have a right triangle, A, B, C, A squared plus B squared equals C squared. If you want this to be acute, so you want this to cave in a bit, then that means C is shorter. So A squared plus B squared must be greater than C squared. This is like not a proof, it's like intuition. All right. Now, since we're trying to show that no 3, keyword here, no 3 form the side lengths of an acute triangle, then you must negate this, negate. What's the negation of this? It's simply that S1 squared is greater than or equal to S2 squared plus S3 squared. All right, so, and also note that I use 1 to be the side lengths on the, like as the 1 on the lesser end of the sign. It's like, doesn't really matter. You can use S2, S3, it doesn't matter. So back to the problem. We can choose from our list A1 to AN to be our side lengths, but we will choose it in a very specific way. We will choose them to be consecutive. So AI plus 1, and then AI minus 1. No, AI plus 2. So for I larger than or equal to 1, we choose to be the side lengths. Okay, so the smallest one you can choose is, well, A1, A2, and A3. All right, so what does it say? You can say that A3 squared is greater than or equal to A2 squared plus A1 squared. And again, without loss of generality, you can choose a2 squared to be on the left or a1 squared to be on the left. And then, but the way we do this, the reason why we have a3 squared on the left is it's going to be very obvious very soon. So yeah, continue this process with the other pairs, the other triplets rather. So a4 squared is greater than or equal to a3 squared plus a2 squared. And then a5 squared, same thing. All right. So the first thing we will try is we can try substituting the first inequality, a3 squared is greater than or equal to a2 squared plus a1 squared, into the next inequality. So we can just do that. So is greater than or equal to a2 squared plus a1 squared, and then plus a2 squared. And that gives you what? That gives you 2a2 squared plus 1a1 squared. And then we repeat this process for every other inequality. So for a5 squared, it's greater than or equal to a4 squared plus a3 squared. But you already have the inequalities for a4 squared and a3 squared, so you can plug them in. So that looks like this. 2a2 squared plus 1a1 squared plus, a3 squared, so that's a2 squared plus a1 squared. Combined to get 3a1 squared plus 2a2 squared. And now I just do it for every single term. So a6 squared is greater than or equal to a5 squared plus a4 squared. And then just add these two. So well, a5 squared is greater than or equal to a1 squared plus 2a2 squared. And then a4 squared is greater than or equal to 2a2 squared plus 1a1 squared. Combined to get, no, this should be, yeah. All right, this gives you, yeah, so we should have put the order in order. I'll just rearrange this real quick. So that's 3a2 squared plus 2a1 squared. And this gives you 5a2 squared plus 3a1 squared. And then repeat, so you can just add these two together, this two, this one, and then you get 8a2 squared plus 5a1 squared. Repeat to add these two together, these two inequalities, and then you get 13a2 squared plus 8a1 squared. So at this point, you can keep going. You can keep going to the last term. The last sequence is, the last inequality is an squared is greater than or equal to an minus 1 squared plus a n minus 2 squared. But at this point, you should stop for a second and see if you can find any patterns, because essentially what we did is we rewrote every single inequality to be in terms of a2 squared and a1 squared. So for the first term, you have, well, 1a2 squared plus 1a1 squared. The second term, for a4 squared, you have 2a2 squared plus 1a1 squared. And then 3a2 squared plus 2a1 squared, and then 5, and then 3, and then 8, 5, and 13, 8. And stop. Do you see a pattern? The Fibonacci numbers. 1, 1, 2, 3, 5, 8, 13. So it seems like you can generalize this to say that a of n squared, this is generalization, is greater than or equal to f n minus 1 times a2 squared plus f n minus 2 a1 squared. and then f of n is just the nth Fibonacci number. And then remember that f1 equals f2 equals 1, and then the defining feature of the Fibonacci numbers is that fn minus 1 plus fn minus 2 equals fn. All right, so this is a quick crash course on Fibonacci numbers, so separate that apart. Okay, so now we look back at the problem, which said that, so we're looking for like more clues and more things to extract from this question, the problem statement. So one thing we can see is that now that we have a1 to an to be ordered, we can rewrite this entire inequality right here. So what's the max from a1 to an? Well, we already defined a1 and an in a list, so they're increasing. So we can rewrite this entire thing as an is less than or equal to n times a1, and that's because a1 is the smallest in the list, and then an is like the largest. All right, so this will help a lot. So we bring that back over here. So from the condition, an is less than or equal to n times a1. Okay, so now we have basically two equations, two inequalities that both have an. So what we can do is we can try to combine them. So let's start off by squaring this inequality. So you square it, you get n squared, a1 squared is greater than or equal to an squared. And now you put this entire equation, plug it right into here. So it's perfect. And then greater than or equal to fn minus 1, a2 squared, plus fn minus 2, a1 squared. And then you can say that this is greater than or equal to fn minus 1, a1 squared, plus f sub n minus 2, a1 squared, because of the fact that we defined a2 to be greater than or equal to a1, which means that, well, if you square it, then the relationship will still be held, and then multiplying by f sub n minus 1 on both sides will give you this inequality. And then if you add this constant term on both sides, f sub n minus 2 times a1 squared, well, you get this. So this is true. Well, I'll just finish the step. And then you get f n minus 1, a is 2 squared, plus f sub n minus 2, a1 squared, is greater than or equal to f n minus 1, a1 squared, plus f sub n minus 2, a1 squared. Okay, so now we can factor this a1 squared out, and then remember the relation of the Fibonacci numbers. So this part entirely equals f sub n, because that's how Fibonacci numbers are defined. This is how this is defined. It's like the defining feature of the numbers. So you can rewrite this as f sub n a1 squared. All right, so combining this entire thing, we get n squared a1 squared is greater than or equal to f sub n a1 squared, and that gives you, well, n squared is greater than or equal to f sub n. And this happens for n is less than 12, less than or equal to 12, because, well, when f of 12, f equals f of n, and where n, when n is equal to 12, this is equal to 144, and then this is equal to 12 squared. If you go higher, f13 equals 100, and no, actually it's 233, and that is greater than 13 squared, which is 169. And then you can prove by strong induction to verify that Fibonacci numbers do indeed grow a lot faster. So you don't have to worry about like the squares, like outgrowing Fibonacci numbers. All right, so what have we just proven? We just proved that, well, in order for this statement to be true, well, n has to be less than or equal to 12. But we do not want this to be true. We want the no 3 to be some 3. We want some 3 because we want some 3 to form the side lengths of an acute triangle. So what we can do is we can negate this inequality. So to be false, well, then n is greater than 12, and then that means some 3 form the side lengths of an acute triangle, which is what we want. This solves the question. So to rephrase this, we could say that, well, for there to be no 3 elements forming sides of acute triangles, n is less than 12 must be true. Less than or equal to 12 must be true. And then the opposite of this is that if there is some 3 element forming sides of acute triangles, then n less than or equal to 12 must be false. If some 3 elements form sides of acute triangles, and then, so this is what we wanted. This is what we wish to happen. So yeah, and this entire statement can be rewritten as n is greater than 12. Yeah, so we're done. The answer is n is greater than 12, and yeah, that's it. Thank you guys for watching, and then don't forget to ask questions if you have any questions, and subscribe. All right, bye.